Thank you so much for. Can you guys hear me well? Good. So if the text I'm writing here is too small, let me know and I'll write bigger. Thanks a lot for the opportunity to speak here. This is my second time in Bangalore, and last time I was here, I learned about quantum groups, and that's what I'm doing these days. It's not related to this talk, but I had an amazing time here last time, and this time also it's been amazing so far. So thank you. So the talk is about an old topic, renormalization group flow. It's a pillar of our modern understanding of quantum field theory. There's been an enormous amount of work on this. I cannot do justice referencing it or doing a proper summary of it. The point I will be trying to make today is that renormalization group flow, in its most general, or one of formulated in a very, very general way, non-perturbatively, is a non-unitary evolution, which is Limladian. So I'll describe that, I'll derive that, and I'll try to put it in context with other approaches. But if at any point something is not clear, please ask. All right, so to give you some motivation, let me tell you what the results are. This is a series of work that, like this is what I'm talking about is going to appear in this work, in this paper that's going to come out soon, but it's built on previous work that I've listed only the ones that I was involved in, but there's a lot more. So the result is this: a fully non-perturbative framework. We're going to be talking about a fully non-perturbative framework for RG that does the following. Has the following nice features from my point of view. So I'm summarizing from my point of view. Different people might take different approaches. So it incorporates and generalizes continuous tensor networks, which is another approach that to renormalization group that is discussed mostly in the context of condensed matter physics, also in high energy physics as well. It has a very, very nice connection to quantum error correction. It provides, I'll try to explain this, a net of approximately local quantum error correction codes. So let me introduce an acronym. QEC is quantum error correction. All right, I'll explain what I mean by this, a net of approximate local quantum error correction codes. And then third, it makes manifest a feature of renormalization group flow that we intuitively want, which is it erases information in some sense. So that has to be made clear about the irrelevant physics, right? So it's sort of a lossy evolution. And in particular, because it makes this manifest, then it's very straightforward to build renormalization group monotones. I'm specifically talking about what is a renormalization group monotone? It's a function that under RG flow is monotonic, either grows or decays, right? I'm not calling it the C theorem for various reasons. We can discuss that, but these are sort of related, intimately tied to that. All right, so these are the features that I'm promising. And in fact, the nicest thing about it is that people in high energy physics do not need to learn a brand new formalism. What I'm describing is basically exact renormalization group a la Polchinski. So it's Polchinski's RG flow applied to density matrices. All right, so is the plan clear? Or at least these are the points I'll be trying to make, right? So this exact renormalization group flow, exact RG, ERG, is a familiar context for in high energy physics at least, more broadly I would say. It was introduced by Polchinski to the best of my knowledge. Maybe I'm pretty sure there was some previous work on this, but what we're doing is like closely following Polchinski, but applying this formalism to density matrices. Any questions so far? So now, again, in terms of motivation, so this is the result. Why is this interesting? First of all, in my point of view, it unifies various approaches to RG. By that, I'll mean that it will include tensor networks, momentum shell integration that we all learned about in quantum field theory, and also holographic RG. That's another context where we talk about RG, and there's like, so there's no unique way of course grading, right? These are different prescriptions, these are different schemes, and they apply to different systems, right? And some systems, some scheme might be more appropriate. But this framework, I claim, is so general that will fit in various approaches. I already said this, but it generalizes continuous tensor networks to include interactions. So at this point, you already know that seems like I'm over-promising, but you have to keep in mind, these are in principle, as those of you guys who are familiar with exact RG, these are it's like very, very general, broad framework. And in practice, for any particular system, if you want to do exact calculations, this is very, very difficult. But formal manipulations of path integral, they make sense. You're all familiar with them in quantum field theory. It could be very, very, in fact, it's easy to do these kind of calculations. That's what we've done for, say, ON model. You could rediscuss, well, you could do the Wilson-Fisher fixed point, all of that in this formalism. So the third thing which in my mind is interesting is that it generalizes the connection that we've seen recently, the past decade, between holographic RG, quantum error correction, and the radial direction in the ball. So I guess maybe I should just put holographic RG and quantum error correction. So it's built, it generalizes that to more general context of quantum field theory. And you'll see what is a compromise you'll make. Yeah, I think that's basically it. And then I'll just point out that this renormalization RG monotones are intimately tied to C theorems. So it provides a new perspective on these. Or even explicit constructions. All right. Good? Any questions about where I'm going? So I'll write my outline. There are three parts. First is I'll try to do a general review of approaches to RG on a lattice. Just put things in context. Where does, you know, like where do these different approaches sit? Then I will talk about what I mean by saying that renormalization group is a net of local quantum error correction codes, approximate actually. Hopefully by the end of the talk there will be some sort of intuitive picture for this you will have. And then 3, I'll actually derive the ERG equation for density matrices and establish that quantum field theory density matrices and establish that it's Markovian, it's scale dependent, it's Markovian means it doesn't have memory, and it's actually a Limlat evolution that I'll write down explicitly. All right. So Markov master equation, Limlat. Good? Any questions?
There seems to be a tension between the desire to be exact and being Markovian.
Correct.
Exact means that you try to take into account, or at least that operator as a whole
Yeah.
So, well, isn't there a tension there?
Turns out no. Turns out no. We'll see. We'll see. So this is exact RG in the sense of Polchinski. These flows are an infinite dimensional space of coupling, so it's very, very formal. I'm keeping all the information. There's a smooth cutoff and all that. I'll comment on the origin of non-unity.
Is weakly coupled by nature? Is that a Born approximation involved?
No. 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 There's no weak coupling here at all. It's somewhat formal, but as usual, ERG discussions are formal. You could be explicit about them though. Any other questions? All right. So let's start with part one, approaches to RG. So of course, our story starts, like my story, like where most talks on, I don't know if red is a good color for this. Most talks on RGs should have this mandatory Kadenov's coarse graining picture. Right, so what it is you have a bunch of spins. This is a classical system for the purpose of my discussion. These spins can take values 1 or 0, 0, 1. So there is a map. This could be a majority vote. And it sends it from the space of 3 bits, so strings of, like 8 possibilities. You can think of it as an 8-dimensional vector to a 2-dimensional vector. It's an isometry. You could explicitly write down it's an isometry. Isometry means that V dagger is a projection, and V dagger V is identity. Okay? So what are the properties of this that are important for me? It's isometric. Isometric means, yeah, okay, I said that. This is isometry. This projection, everyone knows what projection is, right? The self-adjoint scores to itself. All right, and then we think of RG as a multi-layer version of this. So first of all, I have a whole bunch of these V's. In this talk, I'll struggle drawing all these pictures, so I apologize in advance. So you will do these kind of like recursively, but I'm just gonna draw these kind of pictures. So I'm gonna package all of these guys on one layer at one matrix, right? This is also an isometry, right? So I'm just applying these isometries more and more. It's just because I don't want to draw this over and over again in a complicated way. So, yeah, but I have in mind a local structure, hence local quantum error correction. For the purpose, because it's a chalkboard talk, otherwise I would have like explicit 3D pictures. Yeah. All right, so already at this level, I can point out 2 important structures, which is related to this isometric and multi-layerness.
Are you imagining the number of legs to be infinite?
Yeah, I'm thinking of it as, take it to be large. For the purpose of what I'm going to say right now, this is part 1, it's very heuristics, so it's to motivate it, but of course to make these rigorous, you will have to always take some sort of thermodynamic limit to make statements sharp. Actually, here, well, okay. For the part 1 of the talk, thermodynamic limit suffices. Part 2, there will be continuum limit. All right, so what I want you guys to, the way that I want to think about this is that doesn't have to be. Doesn't have to be. Oh, I'm just also imagining. So, okay, so clarification. There are different ways of thinking about RG. And one way of thinking about RG, you think of it as 2-step thing, first coarse graining and rescaling. That is a much nicer thing in the continuum limit. In discrete systems, the rescaling is often realized as just you introduce a cutoff scale and you just change that cutoff scale, right? So these discrete systems don't really have rescaling because scaling could not be discretized. But for the purpose of part 1 of the talk, that's not important. All right. So the structure I want you guys to see is that what this does is, so you have the observables here. You know, all sorts of observables are like operations you could do. It could be a bit flip here. This is all classical, right? You can think of it quantum as well if you want to. But these are like, it could be a bit flip here. It could be all sorts of things. I could do bit flip at different levels. And these observables form an algebra. Algebra of the set of all operations I could apply, right? Now this picture, because these are projections, by sandwiching with V dagger V, I can bring operators down or up, right? So what I obtain is a set of inclusion of algebra of operations, right? And I'm just imagining there are n layers, right? This is the word net. Every time I talk about the net, there's like a set of these guys sitting inside each other. Net of inclusions, right? That's the terminology. A set of subalgebras sitting inside each other. Of course, as I go along, sometimes you don't have subalgebras, you have subspaces, but the main structure I want to think about, because it's not a math talk, is that there is a net of inclusions, of things which are observable. All right, so now the error correction property is also very clear here. Yes, yes. This is the UV algebra, and this is the algebra deep in the IR. Good. So if I start with anything here, I go all the way until I'm left with a single bit, which is going to be either 0 or 1, and come all the way back down, I get two options, either 0, 0, 0, 0, 0, 0, or 1, 1, 1, 1, 1. That is flowing all the way to deep infrared. We have two options from my ground states, right? This is ferromagnets, all up or up, all down. Now this is yeah.
Details of V. It doesn't have to be all down or all up. It could just be any. Take that. Yeah.
Take state 0 here.
Yeah.
Move it back down.
It could maybe become a linear combination of all being 0 plus 1 best.
No, classical. There's no linear combination. This is classical. All classical, right? So there are two possibilities deep in the IR, which is 0, 0, 0 or 1, 1, 1, 1, right? These are the ferromagnetic vacuum. Now, this is an error correction code, a classical error correction code. Why? You could make this formal, but I'm just going to intuitively argue for you guys. If you perform a local UV error, if you flip one of these zeros and ones, as you go towards the infrared, that is washed out with a high probability. It's very unlikely for an error here to flip your final answer, and it gets more and more exponential unlikely based on the number of layers you have. So it's an error correction code. It's an approximate error correction code because likelihood is not, there's a possibility that it still corrupts your situation. Well, that's not a good example. That's not a good argument. But for now, let's go with that. All right? But what you obtain is a net of approximate classical error correction codes. What is the error that's being corrected? Irrelevant local UV perturbations. What is the logical physics of encoded? What is the physical space? The whole like infinite lattice. What is the logical information you have encoded? These are long distance perturbations. So the idea is that UV short range local perturbations cannot mess up your infrared data if the UV and IR have a large energy difference. And actually, if you make the error correction precise, how much, say, so mu is the scale of interest for you, and the UV cutoff is lambda. Mu over lambda controls how good of an error correction code you have. But I guess exponentially good. All right? Yeah.
You're starting at the top with just a single 0. You want to go back.
I said if you do that, but yeah.
If you do that, then just at the second, once you go backward once, there are multiple options for that.
Oh no, this is an isomer. So you see, V transpose, I should say. V transpose is as we go back, so V going forward is a matrix which is, it's not diagonal, right? So it's not a diagonal matrix, and when you invert it, it just goes 0 goes to 1 0 0 0. The other options have no it never happens. They are projected out. So V transpose is a co-isometry. Its range is not the whole thing. It's a subspace. Yeah.
You could have ended with only 2 possibilities.
Yeah, if there's a reconstruction, if any algorithm that wants to reconstruct down, will have to give me 2 options. But there is another way of saying all of this, is that if you scale at any point, and scaling would be if you have 0, just introduce a 0. If you have 1, introduce a 1. But let's not do any of that. But this could be very good. This could be, it could be explicit about construct these matrices, take the transpose, look at the evolution of them, pull them up or down.
Yeah, so you apply V transpose. What is the dimension of the space equivalence? Just 1 dimension?
2-dimensional, because it takes 0 and, yeah. If it's, yeah.
Only 2 of these states will go to something. Others, what about?
No.
Others is
No. So 0 0 0 goes to 0. You know this chart, right? 1 1 1 goes to 1. 1 1 0 goes to 1. Let's just focus on this. There are other ones, right? As you go back, the distinction between these two are erased. So the V transpose will take you only to one of them. You have to pick. In the case that if you write them normally, it just takes you back here. Yeah, that's part of your course grading, right? The course grading is what is it like? Well, yeah, the course grading takes you, yeah.
You assign a definite rule as to what we are.
Correct. It's part of your prescription. It's part of your scheme. Correct.
I mean, that was here. I think we choose which P it is, right? One gives you one P, the other
Yeah,
gives
this
you the
P,
other P.
yeah,
So
exactly. This P already. Yeah, correct.
I mean, one example you gave was a majority vote.
Yeah,
So majority vote in this case, for example, would be specific to my 8 matrix.
yeah.
Then if you take its transpose, going backwards will give you some linear superposition.
There's no superpositions here. This is classical physics. So the matrix, yeah. So it will just, the transpose will give you a bunch of, so the majority vote is a bunch of 0s and 1s, right? This is a classical channel. And the inverse of it will be also a bunch of 0s and 1s, but it's 8 by 2. 2 by 8?
Multiple ones in a column.
Correct.
So that if you apply it to a vector in a 2-dimensional space, it will give you a superposition of 4 things.
No, there's no vector. There's no vector in it. This is class. So your vectors. Okay, I gotta clear this up.
Give an example.
Yeah, give an example. Let me give an example. So in this context, in classical physics, what is a state? A state is a probability vector. It's a state of 3 bits. It's an 8-dimensional probability vector, right? This is a classical channel understood as a conditional probability, right? Or applied to this, and you just go and come back. It's, as Suvrat said, it's very important that we, in this choice, I've already, when I say it's P, I've picked how to come back. I have to make a choice coming back. It's part of the course grading procedure. I mean, in our paper, in this paper, we just worked out this example, like explicitly beat it up. It's pretty obvious, but one of the, this one. It's an appendix, work this out. No. It's, yeah. It's in the paper. What's the question? Can you ask the question?
2 to 1 actually. Maybe that's it. Let's take,
Yeah,
let's
okay.
take 2 and let's try to
So
map it.
yeah, so 0 0 0 1 1 0 1 1, right? V acts on this and it gives you 0 and 1, right? Now, what you should be doing is what you have is a probability P1, P00, P01, P10, P11. This is P, is not to be confused with this P. Let's call this pi, right? So you push this vector, oops, sorry, through this, actually the dual, through the retranspose. Because I'm describing now how it acts on operators. You have to take the other picture, to see how it acts on this guy. And you get a coarse grain thing, which is the result that you get is a two-dimensional vector, p tilde 0, p tilde 1. And this involves, it's a conditional expectation. So it's a sum over pi of, I don't know, like 0, 0 going to 0, 0, 0 going to 1, so on and so forth. Yeah, yeah, yeah. So these are in, okay, I don't want to get into the details of it, but these channels, classical channels, when I say probability distribution, these are conditional probabilities. It means that these are matrices where the rows sum up to 1, right? All the values are between 0 and 1, the rows sum up to 1. The other case is like when the columns sum up to 1. But it's in the appendix. It's really, it's not, there's nothing. But what I want to focus on is that this idea of error correction, that local UV error does not disturb your infrared physics, infrared things. All right. Okay, so this is Kadanoff's coarse graining. Now, this is a classical example. There's a quantum version of this. You could think of it as there are various ways of formulating it, but I'm not going to talk about that for now. I'm going to talk about, so this is a classical coarse graining of a one-dimensional system. There are prescriptions that people have come up with for classical quantum, coarse graining of a quantum system in one dimension. This is called DMRG, density matrix normalization by White, introduced by White. It looks like a one layer of these guys. It's a little bit different. I'll not talk much about it, but this is the distinction between these two. I want to point out two things. Here, what you're doing is applying RG to states. In DMRG, you also apply RG to states, right? This is quantum, that's classical. Now, there's a two-dimensional version of this stuff where you apply RG not to states, but to partition functions. So I want to point out the distinction between the two. You could apply RG to states, which is we take a state and coarse grain its properties. Hamiltonian plays no role here. The other picture is you have a partition function, right? And you apply coarse graining. So this is, for example, how do you want to call this? This is a tensor renormalization group, I believe is what they called it back in 2007 when people came up with this renormalization group. It's a very important piece of work in condensed matter by Levin and Nave. The idea is a two-dimensional version of that, where you have a two-dimensional half integral. Sorry, these are transfer matrices. So we're talking about a thermal classical partition function, or it could be a one-dimensional quantum system. But here I'm thinking of taking the 2D system and writing it this way. And then you have coarse graining, multi-layer coarse graining. You could read this paper. It's one of the very first ones, but there are these kind of algorithms popped up in condensed matter. People have been using them over and over again. It's based on singular value decomposition, similar to DMRG. And it's a way of doing this in high dimensions, right? Which is supposed to be, it's a scheme, singular value decomposition here stands out from the physics standpoint because it's nice in terms of, it's a nice scheme. All right. But I said all of this to say that these have a shortcoming, but hopefully I pointed out this is a partition function and those are states. Now, when I say partition function, we often take the log of the partition function in classical physics, call that free energy, and we talk about the free energy flowing. Or if it's a quantum system, you take the log of the partition function, that's effective action, and you talk about the running of the effective action, the running of the couplings. Sometimes people talk about the Hamiltonian running, right? So I want to put that Hamiltonian running, effective action running, coupling running in this partition function business, as opposed to this. They're related, of course, and part of my talk is going to be about how they're related. But I just want to contrast the two pictures. Any other questions? All right. There are problems with these approaches. As was pointed out with people who are doing actual numerical work. The problems, let me just say them. They're twofold. First, they do not remove all short distance correlations. One way of seeing that, for example, here is that it treats these two legs differently from these two legs, right? So sometimes people say they're not translation invariant, but I don't like that word. There are some short range correlations that are left. Second, these do not apply well to systems near critical points. So if you're near critical points, these do not necessarily work very well. This motivated generalizations of this for near critical systems, near continuous phase transitions. And I'll give two examples. The example which looks like Kadanoff in the quantum case is going to be multi-scale renormalization ansatz, MIRA. And then there's an example that looks like tensor network renormalization, applies to partition functions with the same principle. It's called tensor network renormalizations. I apologize for the choice of words. This is called tensor renormalization. TRG, the other one is tensor network renormalization, TNR. I apologize. People have come up with these names. These papers all have like hundreds of citations, so I don't want to change the names. All right, so MIRA looks like that Kadanoff score screening. So this is now a quantum system. These are isometries, quantum isometries. But then you apply these unitaries in the middle to just make sure that these legs are not treated differently. And if you run this many layers, it's nicer. This is, let me just at least do some justice. This was introduced by Gifford Vidal. Yeah. Yeah, numerically nicer. Correct. Absolutely, absolutely, absolutely. So you could just not worry about the physical interpretations of these things. You know, people say that these are called disentanglers. They're essential for recovering translation symmetry, blah, blah, blah. But you could just look at numerics, and these outperform these kind of methods. Of course, this method you could apply to 1D quantum systems, well, DMRG as well. Well, they perform better with the standard ways. People have improved on these significantly. So I'm just describing the most basic thing. So you could apply this, of course, to partition functions. This is, as I said, so this is MIRA. Let me call this MIRA. This is called TNRG, Tensor Network Normalization Group. It's Glenn Evemley and Gifford Vidal as well. They work pretty well as well. Now, already at this level, these guys made a beautiful observation. The observation was this. If you take, can you see here, is this fine? If you take one of these, so this is a path integral, this is one of these Euclidean realizations of partition functions. Just cut open a boundary, right? So you have these kind of things. And you apply your TNR, renormalization to this guy. The presence of this boundary messes up your there will be residual things as you perform these steps due to the presence of the boundary. What these guys prove is that if you apply a TNRG to the setup where you have a boundary, on the boundary deep in the infrared, you get a Mira. So this was a very conceptually pleasing thing. Of course, those of us who work with path integrals, this is very familiar to us, right? So they said that if you apply TNRG, they establish this in the infrared, you get Mira. Is that good? Because we think of it, but every time you have a path integral, you cut open a boundary, we think a Hilbert space lives on that boundary, right? So if you're doing some sort of a renormalization to your theory, that should be reflected on some flow of states that live on that boundary. Now, what is surprising is that Mira comes out. Well, I mean, that's not terribly surprising because the algorithm they constructed for TNRG was basically like Mira, applied in the middle of the partition. Yeah. Yes. All right.
Does this identification from TNRG to Mira also holds for some state prepared by some weird Euclidean path integral? For instance, like if you consider thermal state, or maybe like consider some bunch of transform matrix, but like removing one of the transform matrix and glue them with some other.
So, right. So if you take just an arbitrary, now I can use the word path integral, but these are discretized, right? Poke a hole in there, you're going to get the Hilbert space, and this is going to apply some coarse graining that looks like Mira. You only literally get Mira if you take a limit of infinite line and all of that. But the picture is, at least in the case that you have a line, it's pleasant, right? Like it puts together the two pictures. Otherwise, you get some flow. This is also, I think I should say, this is also the same authors. Len Evelyn Vidal. 20.
So you mainly focus on pure state transformation rather than mixed state?
No. For now, I just wanted to point this out. I'll come back to all of this. All right. Any other questions? How am I doing? I should speed up. I should speed up. Okay. So now what is nice is that in this TNR and Mira, there is error correction, a quantum version of what I said. There is actually a local, a net of approximate local quantum error correction codes as was established. So let me just say this, a net of approximate local quantum error correction codes. Mira is, maybe I should say that, Mira is, this is a paper by Isaac Kim and Castoriano from 2017. I'm just gonna heuristically draw it for you guys. There is Mira here, okay? So this is Mira, this is the UV, this is towards the IR. So they should think of these as things like that, okay? What these guys showed is that, so this is the UV, this is the IR. So you could think of some isometry that takes your HUV to HIR. They showed that if you make a local error in the UV as you go towards the IR, it's unimportant. So I'll clarify that. If you have an operator here, for example, some operator O, you could define, for example, in the UV, this map. This is the map that renormalizes this operator. So we're doing everything at the level of operator. This is a scaling operator. So deep in the infrared, if you end up with a bunch of operators that are, well, I haven't explained that, but this operator deep in the infrared, it has positive spectrum. Deep in the infrared, its eigen operators will survive. Eigen operators are lowest dimension. And actually, The eigenoperators are nothing but scaling operators. So if this is like this takes you from scale lambda to E2 minus lambda, this is gonna look like delta. So these are primaries, conformal scaling. I should call it conformal primaries. This is scaling operators deep in the infrared. This is the quantum channel. This is actually Markov semigroup. As you apply many times, there's a spectrum. The spectrum turns out to be positive in this case, and the lowest lying ones survive. The identity is the unique invariant of this flow, right? It means that the operator dimension 0 is unique. That's just identity. Similarly, in the Heisenberg, this is a Heisenberg picture. Sorry? It's not sub I, sorry. This is R that takes you from lambda to E to minus S lambda. It's a super operator. It's a super operator. It maps operators to operators. Yes. So W, in the case of Mira, it's just a bunch of isometries and unitaries stacked together. Yeah, and then you repeat that many times to go from scale lambda to E to minus S. I understand that, yeah. Exactly, you could push them up towards the IR or down towards the UV. Now, yes. I haven't said that yet, but yes.
Is a W maps a UV to IR or IR to UV?
If W is an isometry, W takes you from states from UV to IR.
Okay, so
however, in the Heisenberg picture, if you sandwich on the right with W and W dagger on the left, it brings IR operators to the UV.
Okay, so R or UV is...
Did I write this incorrectly? Yeah, I wrote this incorrectly.
Oh, okay, got it.
Sorry.
Thank you.
So I wanted to write the other way around. Yeah, thank you. Yeah, so as you switch from UV to IR, as you go from Schrodinger to Heisenberg picture, I'm being sloppy. I have my note correctly. Any other questions? Now, what is error correction? Those of you guys who are familiar with quantum error correction, you know the big master equation that you have in mind is called Nil-Laflamme. Nil-Laflamme operator, Nil-Laflamme equation. Yeah.
Why are these deltas real, or do we know they're real?
Oh, no. Based on what I've told you, you don't know any of those. But turns out in these examples of Mira is a very explicit construction. These are real. Actually, even the positivity of them is not clear. So one of the interesting things is that the first paper we wrote, we tried to formalize this in the continuum limit as a bunch of sequence of maps. And what is interesting is that these are sort of axiomatically put in there. These are requirements we want. I don't have a deeper intuition to offer, unfortunately. I'm perplexed by that as well. I can tell you one thing. The condition that these are real, the eigenvalues are real, is the condition that as a quantum channel is self-adjoint. It's a quantum version of detailed balance. So that is sort of physical, but positivity of the spectrum, I have no idea. Actually, no, that I'm also lying. There are ways to argue for that based on more fundamental things. But for now, just imagine Mira is a very particular map. Construct this, and this is what you find.
And if you actually had a CFT, these 4 deltas would be the scaling operators of that CFT.
Correct. As a matter of fact, people do read off. They take lattice realizations of theories that in the continuum limit have CFTs. Using this method, Gifford and friends have read off like all the, this is how you use Mira to read off deltas. All right. Any other questions? So what is error correction? Unfortunately, I can give a whole talk on error correction in the Heisenberg picture. Quantum error correction, in my opinion, should be done in the Heisenberg picture because it's a lot nicer. But here's what also let me just make a cryptic comment for those of you guys who care about this. Every time you have an algebra inclusion, that's could be understood as an exact quantum error correction code. All right. So if you have an operator, I said that WW dagger is a projection. Projection to what? Projection to the code subspace, right? So Nil-Leflam equation tells you that if you make an error here, right? And then there is a projection corresponding to this level, IR physics. This error could be corrected, so this UV could be corrected if the following property holds. P, that projection, OUV P is almost equal to P. If it's equal, that's exact quantum error correction. If it's almost equal, it's approximate quantum error correction. Meaning that the effect of this does not disturb. Is in the code subspace, it either acts in the perpendicular directions, or small. The action of it projected the code subspace small. So this is the approximate Nil-Leflam equation. I encourage you guys to think about Nil-Leflam and quantum error correction in this form, operator form. So, yeah, if you take an error, sandwich it with P and P, right? It cannot have a component. It has to be, components have to be outside. Yeah, so that means that it's equal to P. Because P means trivial operation, doing nothing in the logical space. Oh, you could check this, that if Mira is a concrete network. For Mira, I'm talking Mira, right? So this is, I'm talking about the content of this paper. For Mira, this is a concrete network. You could show that, and then the errors here are controlled by S. How much what is the scale of IR divided by the scale of UV? Because P depends on S, right? How far you go. All right, so this was to say that again here you have a net of approximate local quantum error correction codes, and they get the error correction property gets better and better as you go further and further into the IR. Yeah, absolutely. That's just the physicist's intuition of UV physics. Is UV local perturbations is irrelevant. This is a quantum error correction context for that. Or if for those of you guys who know holography, you've heard these terms that erasure, local erasure in the UV could be corrected. It's the same thing. As a matter of fact, that's my next point. So in holography, you're familiar with.
Where is the dependence of the isometry and the unitary here?
Say it again.
Where is the dependence of the tensor content of isometry and unitaries?
All in this isometry.
So it doesn't affect the Nil-Leflam.
That P is W dagger.
Oh, okay. Okay, and the this approximation doesn't depend on the tensor content.
Of course it does, but if you want to get a general bound, right, that's independent of it, this would do.
Okay, thank you.
Of course, you could fine-tune the tensors such that particular local errors don't mess up your physics. But what we want is that no local error does it. Therefore, we should rely on none of the microscopic details of W, but just take the worst case scenario. Now next, I'm already moving towards the continuum limit, but let me talk about holographic RG a little bit. So you've heard these words, or maybe you've read these papers that establish that renormalization group flow in holography is radial evolution. For example, I recommend reading the paper of Jan de Boer, Verlinde. That's just a very natural thing. Well, I'm not going to explain that. There's also the statement of quantum error correction in holography you guys hopefully have heard about by, like, for example, Almeri, Dong, and let me just say it, Almeri, Dong, and Harlow. The picture is very much similar to this. It's very similar to this. You have this UV thing. You have this RT surfaces that we know about thanks to Tadashi and collaborators. If you make an error here, it does not affect stuff here. In fact, if you ask what is the Nilaflam equation, it's this. If this is the P, so to every, there's a projection. So you have a net of these error correction codes, right? If this is the projection that corresponds to performing RG from this point to this point, you put an operator O here. P, O, P is P. It's exact quantum error correction. Now, is there a question? There's immediately a point for comment. Here, I had to flow really in the infrared for me to see this. Here, I can put the operators arbitrarily close, and this property still holds. The commutators vanishes exactly. That's some large N magic that makes geometry local here. Here, what's happening is that if you take an operator here, an operator here, the commutators get small as you push them far apart. So there's like some sort of CMIRA has the skeleton of a geometry. It has this, in words that high energy people love, it has perhaps the super ADS scale holography. If you want to make holography sharp, you have to take some sort of large N plays a role here. We've discussed that in our paper, but I just wanted to argue for it qualitatively. So at any scale, if you perform RG, there's a quantum field theory living here. This is the RG float quantum field theory. These are now, as you go from this scale to this scale, this is a W. This P is going up and coming back down, right? It's sort of like taking, this P brings operators in the UV, sorry, further IR down to the lower scale. Oh, there are various ways of discussing it, but perhaps the more familiar thing is that if you put the commutator two operators here, that's zero. For me to get zero commutators over there, I had to separate the operators by a lot. Here, I just get them. This is like locality in the bulk, right? The fact that I want a quantum field theory living here and I should have operators on constant time slice commute, this is related to that. Again, like I understand that in our paper we explained that a little bit better. I did a poor job here. All right, any other questions? Okay, I better speed up. Good, so what did I do? This is sort of the end of part one. I went through a whole bunch of methods that people use in condensed matter. There were two types of things, renormalization of states, the renormalization of partition functions. This, as a graduate student, really confused me. Why are we talking about Hamiltonians when we are doing RG2 states? But this is the story, they're connected. We also mentioned the quantum error correction connection. If you do RG, the UV physics is noise. That is protected, and the infrared physics is logical data that's protected against the noise, right? Irrelevant versus relevant. And then we commented on holography and the connections to mirror, similarities to mirror. All right, now we want to go to the continuum limit. Why not take a continuum limit of this business and we'll be done? Turns out that people, I'm just not going to write it. I'm going to say it because I'm short on time. People have taken the continuous limit of Mira called C-Mira. Lots of people have worked on this. I want to point out Tadashi's work, which I'll comment in a second. So let me first talk about some shortcomings. People have taken the continuous limit of this. It's called C-Mira. they have taken the continuous limit of this. It's called CT and R. C-Mira, hopefully you guys are familiar with. So some of you guys. It's a unitary flow that washes, that coarse grains the system. It's comprised of two steps, scaling, because we have it in the continuum limit, and disentanglers are this particular interaction that looks like some kernel phi p plus the Hermitian conjugate. My favorite Mira is actually something called magic. My favorite C-Mira is called magic C-Mira. This is also, not surprisingly, Giffer Vidal. I absolutely recommend this way of thinking about it. It's a beautiful, beautiful paper. It's a unitary, yes. I do not have the projections yet. Very good point. Yeah, I'm going to comment on that. But so let's put that quantum error correction aside for a second. So C-Mira is unitary. Unfortunately, it really works only for free theories. Attempts to include perturbation theory, even at the first order, are confusing. Now, that might be a controversial thing depending on who is in the audience, but I'll just tell you that the second order will definitely confuse you. So you can't do interactions properly in Mira. Now, I want to point out Tadashi's work. Tadashi using holography, Tadashi and friends, collaborators, using holography, they motivated another way of thinking about interacting C-Mira. That will not be the topic of my conversation. Okay, but the standard C-Mira is unfortunately suffers from this fact that it has to be Gaussian. All right. CTNR, you might ask, what is CTNR? Let me just quickly say what it is. It's something very, very intuitive. You take the field f of x, phi of x. This is Euclidean path integral. You define phi of lambda of x as an integral over dy of some kernel. So it's just smoothing of the field with class of smooth functions that are labeled by this, and there could be Gaussian, there could be whatever, right? Unfortunately, CTNR also applies, it's also only nice for free theories. Now, if there's a conversation, I can tell you why. Here comes the surprising part. Two things. The question that was asked earlier, why is C-Mira unitary? Where is the error correction? Right? Point two, turns out that CTNR in the presence of a boundary does not give C-Mira. That's also another paper of Giffer and friends. So where is our partition function connection to the boundary? Right? Good? Is it clear at this point? So the review part of the talk is over now. I'm just going to present results from now. First, I'll resolve this issue of unitary versus isometry by working out explicitly the approximate quantum error correction code in C-Mira. Of course, very explicitly, you have to look at the paper, but is the idea clear? All right. Any other questions? How much time do I have? Oh, okay. Well, I'll get to the main point, so that's good. So part two. C-Mira is a net of approximate local quantum error correction codes. This is in this paper, 21, 12, 05, 009. All right, first thing you do, and as I'm going to explain it, you'll see that how close it comes to holography. I'm going to do something that I'm going to make an assumption that does not hold for free C-Mira. Okay, this is I'm going to motivate it. Imagine you have a system with a Hamiltonian where you have a bunch of low-lying states. These are IR low-lying states, right? So light operators. And then there's a gap, and then there are heavy operators. So there's a gap. The first, and the answer to the question that was asked, that why is this unitary and still there is some sort of a, we're saying that we're comparing it to error correction, is that you cannot, in a theory that's continuum, genuinely continuum. A local density matrix has too much information. As a matter of fact, using the operators that act locally, you could do to reach leader, you could create anything. So you have to not, because you have arbitrary UV local stuff in the continuum physics. So it's unfair to require that you could correct for arbitrary local errors. What you do is you pick your light operators. Let's say there's a gap so that there's a sharp distinction. You select a group of these guys. Now, what happens is precisely this. There's a region. If you perform a perturbation here, which is generated by some of these light operators, and the same structure holds. Oops, sorry. So you do not get a sharp RT surface, but the width of this is controlled by the gap. So operators here and here commute, almost. If you want them to really commute really, really well, increase the gap. Make the gap large. Now there are two stages. So let's track the evolution of an operator as you flow towards the IR. You pick one of these operators, you insert it here and flow towards the IR. First thing, this is similar to what Kim and Castoriana saw. Stage one, the support of the operator shrinks. The support of the operator as you go from here. So let's say it's supported here. And the next step is supported here. Shorter and shorter. Until you reach the end point. At that point, it starts falling off exponentially fast with the dimension, which is related to the scaling dimension. So you don't get a sharp, like, local thing. Yeah, sure, for sure. This is heuristic picture. This is to be understood as C mirror. So to motivate the discussion, but you could literally do this discussion. What we did was that we literally tracked the evolution. We see two stages. In stage one, the support shrinks. That's why I was drawing this picture. Stage two, the norm of the operator decays. Yeah. Yeah, exactly. This is the distinction between the holography and C-mirror, or these setups.
What happens? You start with a light operator and you go, or you start with a heavy operator.
No, light operator.
You start with a light operator.
Yeah. And then you flow towards the IR. First, in C-mirror, the support of it shrinks until the support of it becomes very, very small, of the scale of the cutoff of the theory, right? Then past that point, the norm of the operator starts decaying. And the decay of that is controlled by the lightest dimension of the scaling operator. Yeah, you need to always, so what we did was that in C-mirror, we picked a particle, so there's no gap. We picked a particle, we classed them into low and heavy. We picked a light one, and we track it to get all this structure. Now, if you want to play around with the form of the structure, we learned that the second stage is not desirable from the point of view of holography. If you want that to be suppressed, that to be very short-lived, large gap would do the job for you. If I don't have a C-mirror for that, but if on my head, if I assume something like that, it would do the job. This is motivation. Motivational. This is motivated. There's no causal wedge here, right?
So can you tell us the precise statement?
The precise statement is this. The operator, as it evolves, there are two stages to evolution. First, the support shrinks until it reaches the cutoff of the theory. Past that point, the norm of the operator decays. That's the only thing.
Let's say I start with the operator, which is a linear combination of two light operators.
Sure.
And what happens? The support shrinks till it becomes a linear combination of two operators supported with that.
Yeah, absolutely. Absolutely. Yeah. So when I take, let's say I have an operator integrated O of x, U of x from over some region here, A. As I perform, as I go to the IR, that this region, the size of the region shrinks. No, no, no. So I can track the evolution of each operator, right? So in particular, this is a particular operator. I can track its evolution, and I can see where it ends up. It has two stages. The part that is perhaps counterintuitive is that there are two stages to CMIRA. First is coarse graining, and then you rescale. Under both stages, the support of it shrinks. Mm-hmm. Yeah, absolutely.
And now what I'm confused about this statement is it's 2 for F1 and it's 2 for F2.
Yeah.
So the operator shrinks to a delta function. It doesn't look like F1 plus F2 is shrink to a delta function.
Why not?
It's linear, so it at least shrink to a sum of it.
Sure, but it's
Then
still local.
If I take a continuous F, like I take something which is the basis of F, it's like a continuous distribution, then it will not shrink at all.
You cannot arrange for any perturbation of that type to be low energy. So basically, yeah.
So that sounds like the main statement. Somehow if I take the basis that you're looking at of Fs, if I take something that looks like a linear combination of so many Fs that the final
Yes, of course.
that will be high energy. But that sounds like somehow the statement is that
One simple, no, it's not a deep statement. One simple statement is that because this light set of operators has a finite dimension, this finite dimensionality already puts a bound. Now, of course, if you want to include this light operators to be very, very large set, it will mess up the argument. But the dimensionality of this subspace is controlled. So another way of saying that the dimensionality of this subspace effectively renders this story finite. So it's like a coarse grain.
some operators also get mapped to 0, I guess.
Well, nothing is mapped completely zero. It's an approximate quantum recursion.
Projection.
It's approximate. There are these wiggly lines. It's approximate quantum recursion. Nothing is exactly projected. There's no UV insertion that literally commutes with all the things in the IR.
Some operators can start decaying before you.
Sure. Well, we're considering the worst case scenario here. To make a statement about all operators, all errors, all local errors.
But it is true that some operators can have their norm decay a lot.
Yeah, absolutely. You could coarse grain in such a way that you just some errors are never playing any role. Yeah, but what we want is that we want this method of coarse graining to show that this method of coarse graining protects about some generic set of UV errors. Now, again, yeah, okay. This is motivational. I just wanted to, this was a problem for us that we had to sort out, and we took this CMIRA, actually magic CMIRA, and beat it up. So we worked at, if you look at the paper, it's a very detailed calculation. You take while operators, you flow them, you establish this, you establish the errors, and you keep track of nil left. There are theorems in the paper. So if you wish, I just don't want to present them.
If you consider the product of two quasi-local operators, does they start decaying as long as they pass this kind of well?
So the issue here is that the set of light operators, they don't form an algebra. As you probably know, if you take two operators low dimension, you keep multiplying them, you're going to produce. So up to a certain number of multiplication times is okay, because if you arrange for your errors to be small, as you multiply more, maybe those errors are just getting larger by coefficient.
Sorry,
as long as you have a separate control over how small the error is.
What I meant is just as like let's say two operators at some distance, and consider two product of these.
Oh, you want to be separate?
Yeah, yeah.
But that's not a correctable error.
Why?
Because you separate them by long distance. So that's not a UV.
No, I mean consider two intervals. And each operator supported on each interval.
Yes.
And naively for each operator, this up to this scale, they start decaying. But if you naively consider some holographic picture, there could be some entangled wedge connecting these two.
Are you worried about this kind of stuff?
So I was wondering, where does it start decaying? Whether above the causal wedge or above this entanglement wedge.
In CMIRA, this picture doesn't hold literally. If you try to construct such a picture, it will be very fuzzy, and you could do the calculation and figure out, I don't know the answer to that. But it's a very sharp calculation. It's a very well posed, it's Gaussian theory. There's nothing secret about this.
Thank you.
You could do the calculation. I do not know the answer to that. All right. So this was kind of like, I did not provide much details. I just wanted to say there is free theory CMIRA is all good, at least with error correction. Now I get to the important part of the talk. Maybe I should pause here for questions. I'm going to start part 3, which is exact RG and this Limladian business. Oh no, CMIRA is a unitary description. It's just the input is unitary. Maybe you're asking me, I don't see how these P's come about. Maybe that's what you're asking. Yeah. So over there, we in the paper, I can say in words simply what it is, but what we constructed are these P's, these maps. What it is that because you take a set of these light operators and you just track the flow of these guys, this is like a subspace of that. And the unitary does not guarantee that this subspace is flowing to the same sort of dimensional subspace. If you track that, because you look at this, focus on this subspace, you effectively get this approximate isometries. This is not very good, I understand, but you have to, I don't have a very good explanation of this. It comes out of Weil algebra. You just write down the evolution of unitary Weil operators under this and see how you track it. All right, any other questions? Now I want to talk about something that's exact RG of Polchinski done in the presence of boundaries. This is very, very here, even though the calculation is very exact, but there's no general principle, right? What I'm going to describe now is very general. All right. So a very quick discussion of what exact RG is. Or ERG. As I said, to my knowledge, it was introduced by Polchinski. Maybe it goes back to other people as well in other contexts. So let me argue for it with a simple setup. Even though I'm going to write down a scalar field, it doesn't have to be scalar. It could be any spin, any system. So I'm going to take a scalar field. And I'm going to add some interaction term. And then I'm going to add some sources like this. All right. First thing Polchinski does is that he says, let's take the kinetic term and introduce a smooth cutoff. This is the UV cutoff lambda. You're going to suppress the Euclidean momenta. So this is, I'm going to formulate in Euclidean space. So what we're talking about is Polchinski's RG, ERG applied to Euclidean path integrals, in particular the partition function, right? So this is not a state picture. This is just partition function. I'm going to call this S0 as opposed to S interaction. All right? This function is picked in the following way. This is 1, this is 0. This is the cutoff. K is basically suppressing the UV modes. Now, this is a smooth function. Why is it suppressing the UV modes? If K is like this, for modes that have momenta much larger than the cutoff, this is large. When S is large, E to minus S is small, so it does not contribute to the partition function, so the high energy modes are suppressed. Good? Was that quick? Okay. Now, what do you do? you take lambda del lambda of the partition function. This better be 0, right? And you learn, well, you figure out that this is lambda del lambda of this S naught term plus lambda del lambda of S interaction term. I don't have any boundaries. I'm just going word by word over what Polchinski said. Good? Are we good? So the running of S naught, we're going to eat it in the redefinition running of S interaction. How do we do that? There's a trick which is Schrödinger-Dyson. It's the following. So Schrödinger-Dyson says, if you take some operator, O of phi, del S0 del phi is del O del phi minus O del Si del phi. This is just a consequence of the fact that you want the path integral to be invariant under field redefinitions. Field is a dummy variable in the path integral. Using this, you rewrite. So lambda del lambda of S naught explicitly depends on K. You rewrite this term in terms of S interaction. And now you have an equation that you have to satisfy only for S interaction. That is Polchinski's RG equation. What is that equation? The fact that this has to be 0, you massage this to the right. I'm going to write the right-hand side of it. This becomes del Si del phi, lambda del lambda of let's do another. Let's define G minus 1 to be K minus 1 del squared so that I can write this simply. There's a second term. The traces mean that integral in the over the whole Euclidean spacetime. A inverse box. Yeah. Yeah, that's box. Sorry, what is the question? This is del mu del mu. This is, by the way, Euclidean. Everything I'm saying is Euclidean for now.
I know. I was wondering if you first integrate by parts and then put the key. You first try the kinetic term as phi box phi.
Oh,
then you put the
because I don't have any boundaries as these are equivalent, so it just will change an extra term. It will change this piece here. It will change. There will.
One of the details will act as the key as well.
Correct. But up to the boundary terms, and that boundary terms does not change the physics. Blah blah blah. Yes, absolutely. Yeah. So, but this is the idea. Hopefully, you can see the idea, right? So you introduce a smooth cutoff. You do a variation. You use Schrödinger-Dyson to relate del lambda of S0 to functional derivatives of S interaction. You have to now solve this equation. Lambda del lambda of S interaction is something related to S interaction. That is. Oh, I'm sorry. I'm so sorry. Thank you so much. Yes, thank you.
How you use the Schrödinger-Dyson exactly to get this S naught. The only thing that appears in the Schrödinger-Dyson is a phi derivative of S naught. You don't have any phi derivative in what you want to substitute.
I don't have any phi derivative.
There is no phi derivative in this thing that you circle.
Very good. So let me write this down. So lambda del lambda of S naught is minus half del phi of S naught, lambda del lambda of G del S naught del phi. Let me explain this. How do I get this? What I have to do is I have to take it lambda del lambda of K minus 1. I first observe that is K minus 1, lambda del lambda of K minus 1. This K minus 1 acts on one of the phi's. I put this K minus 1 on the other one. Now I use Schrödinger-Dyson. This is a trick that's used. It takes some processing why we're doing this, but yeah, this is it introduces in some intrinsic non-locality as is expected in non-perturbative RG. It comes from the fact that you're taking del squared to the power of -1, but yeah.
Focusing on the Lorentz invariant theory.
At the end of the day, what I'm going to say holds for showing you Dyson type, so Lorentz, Euclidean, everything. Right? The interpretation is different.
I mean,
however, for now, I'm just talking Euclidean.
I'm a bit concerned. So, like, if you so with this cutoff, I guess you're assuming that the high momentum modes corresponds to high energy modes.
I'll get there. I'll get there.
Okay, thank you.
Okay. Any other comments? This is the way that Polchinski did it. All right. So next, what we're going to do is we're going to, as we said, this actually connection between that was observed between TNR, tensor network normalization, and Mira. If we do this in the presence of a boundary, we wonder if we get something that looks like Mira. So now I should cite actually your work. This is way overdue. So Jackson, Fliss, right? Onkar and Rob, they wrote this paper that I should have listed from 2015, 17, something like that, 2017, 15. That did what I'm going to describe. They wrote more than this. Like they wrote a couple of papers related to holography, blah, blah, blah. But this is the paper that sort of motivated our work. So we're going to do ERG in the presence of the boundary. I'm going to formulate it in a way that perhaps is very similar to what they did, but change of variables, perhaps. First thing you notice is that your k minus one function now no longer can have this structure, because it will make the in the presence of the boundary, your boundary value problem is ill-posed. So they proposed that you take k minus 1 to be like this. This is just the spatial part of the Laplacian. So just suppress the spatial part of the Laplacian. Okay, a couple of comments here. What I just described, as Polchinski did it, had one step, just lambda del lambda. What you could do is you could introduce a variable z here, that is the physical scale of interest. Now you have two steps. In the first step, step 1 of RG, you send lambda to e to minus s lambda. As I described you with this, you do the ERG. In the second, there's a boundary term now, right? There's now a boundary term because of this. So I have to add that to my action. In step 2, you use a symmetry of your theory. The symmetry of the theory is this. If you send z to e to the power of z, lambda e to sz, this, and then phi transforming under while rescaling, if there are, this is a symmetry of the action, so it's a scaling, right? If there is no anomaly associated with it, it's a symmetry of, it's a quantum symmetry. So you first bring the lambda lower, then you rescale using this transformation to bring lambda back where it was. The only thing that changes now is z by s, and s keeps track of how much you've been flowing. So if you want this symmetry to be more explicit, with some boundary conditions phi over here, you have a wave function that depends on lambda and z. This is d minus. Of course, I'm talking about the scalar field, but I don't have to. Okay, this is a symmetry. All right, so you do these two steps, and as we learned from Fliss, Robley, ooh, I'm pronouncing 5 minutes. Sorry about that. As we learned from them, what happens is that if you do this in the presence of a boundary, you pick up a boundary term. And it looks like this. Let me write down the evolution. Del S of 5 omega of J will be phi minus trace over the manifold of omega of J. Here, there are 3 terms. First one is a beta function term. I shouldn't, well, okay, let me call it J. Then there is a scaling term, we explicitly calculate it, and then there's a disentangler term. So what you obtain is a unitary flow. Explicitly, you obtain a unitary flow here. You could identify this, as these guys did, the scaling operator, and you can identify the disentangler. Of course, the details of disentangler depend on the interactions. All right, I can write down this a little bit more explicitly, but I'm out of time. You can always refer to the paper. Let me actually write, well, just Google unitary networks, Rovli and Onkar. I should have had the reference here, sorry. Okay, all right, so last couple of minutes, I'm just gonna tell you about what happens when you do this for a boundary, 2 boundaries. Oh, by the way, another thing is one of those references is that we took this, we broke the, because C-Mira is non-relativistic, we used 2 different coarse graining Ks for time and space. Under this procedure, we obtained C-Mira on the boundary, magic C-Mira. So that was the content of one of the papers. Now, this is, yeah. How would I do it? I probably will have to think hard, but the formalism formally holds. Yeah, I think that the issue would be, of course, boundary conditions. Do you have any thoughts on this? I think it will not conceptually be different, but you have to be careful. I mean, gauge theory in the presence of boundaries is a little bit tricky. But yeah, I don't think that conceptual. Did you guys work out any examples of that? Yeah. I think that's a very good question, and we've just simply not looked at it. My expectation, naive expectation, is that the formal prescription will go through. I'm sure in the context of ERG, yeah. Okay, that's a very good question. I have to look at. Okay, so as the last couple of minutes, let me just say the content of this Lagrangian business. So now we said, let's do the calculation with 2 boundaries. All right, it's a density matrix. It's a Euclidean path integral. I'm going to tell the story as if it's Euclidean path integral. It doesn't even have to be. As a matter of fact, if I have a path integral which is Z2 symmetric, it could be a pure state, and I'll still flow to something that's mixed in general. All right, so you do the same thing. Now, previously, these boundary terms, what happened was that the way we got that thing is that as you do perform the path integral, you're going to end up with some operating exertions here. That's what led to unitaries. Now, you're going to end up with a bunch of boundary terms here, a bunch of boundary terms here, but because ERG is non-local, you're going to end up with boundary conditions with operating exertions before and after the density matrix. So they're going to sandwich the density matrix in the following form. You literally follow Polchinski's ERG, you obtain the following equation. There will be a unitary part, which is the same principle that we saw before. There's now a non-unitary part, and structurally, it looks like phi rho phi terms. There are pi rho pi terms, phi rho pi terms, and so on and so forth. Of course, you end up with phi squared rho commute these guys with a minus sign to make sure that the trace of the density matrix is normalized. Once you repackage everything, there's a very elegant way to represent this. You define a creation operator at scale lambda. It has a definition. Let me just now write it. We define it. And this d of rho will take the following form. It will be an integral with a kernel, which is just dependent on lambda, the lambda of log of k. So this depends, this is scheme dependent of p. Now, there's gamma plus a rho a dagger. I have to subtract this part to make sure that this unit trace plus gamma minus a dagger rho a minus this. All right, I'm just gonna stop and comment. This is the result of a calculation. There's not extra input than simply treating Polchinski's methods in the presence of boundaries, and the result was surprising for us. First, look at the structure of this. So there's a non-unitary term that comes up. The non-unitary term has this very nice structure. What is this? This kind of equation, this kind of Limlad equation is famous in quantum optics. People have looked at this. This is an emission term. Your system is losing energy to the environment. It's unclear where the environment is here. This is an absorption. This gamma plus and gamma minus are the rates, decay and absorption rates. As a matter of fact, if you do this for a path integral with some width beta, these guys are 1 plus minus, cotangent hyperbolic beta omega over 2 plus minus I. If you have a Limlad equation like this, there's a condition called quantum detail balance. It relates the decay rates to absorption rates, and it ensures that your system will equilibrate. Well, it does a whole bunch of things. Turns out that these values are the right values to have quantum detail balance. So that's good. That's a nice interpretation. The Limlad equation is scale dependent. So it's not a Markov semigroup. You guys know what that is. So you would have to scale order when you exponentiate. The system is distributive, it's memoryless. And one last comment is that any distinguishability measure of any set of states, say take two states and relative entropy or fidelity, it's obvious that's monotonic under this ERG flow. As a matter of fact, if you compute it in simple examples, you could keep track of it, how it flows. You get a whole zoo of renormalization monotones, fully non-perturbatively. Now, why am I not running out claiming victory for C theorems in arbitrary dimension? Because first of all, like any other C theorem that we've ever constructed, of course, ERG is scheme dependent along the flow. So any quantity you define along the flow is going to be scheme dependent. This is one way we can here define all sorts of things, but they're going to be scheme dependent. Now, we're interested in a scheme that at the fixed point, in the vicinity of the fixed point becomes scheme independent, or there's a canonical choice for it. And also at the fixed point, we recognize a central charge or measure of degrees of freedom of the fixed point, and on top of it, we want it to be stationary. So now it becomes a game of searching for such monotones. I'll stop here. Thank you.
There were a lot of questions during the talk, but any further questions? Typically, you would say it's the most unique route.
Yeah, so this is a very, very good question. It's related to that similar thing that we're saying that we're not, the cutoff is smooth. We're not discarding anything. We keep track of all the information, but we suppress the UV modes. Now, after rescaling, it still leads to some non-unitarity. It's unclear to me where the environment is. That's very good. That's a very good point. I want to think about it that way, similar to this, the similar thing that I want to think of these as some IR physics, that I'm only really keeping track of this stuff. Yeah, that is what I would like to say, but I have not quite done a calculation. We have not done a calculation that makes that very clear. I have no idea. Yeah, I'm not familiar with that. Sorry, I do not know about that.
Okay, let's thank Nima again.